Oh, nice. Okay. Hello, everyone, and whoa, that's loud. Welcome to Astronomy on Tap. Thank you so much for, yeah, that's cause for applause. Absolutely. Thank you so much. Thank you so much for coming tonight. As we always do at the beginning of these events, we're going to start with trivia. So if you want to play trivia, please come get a sheet and a golf pencil down here at the front from Bo, who has them. And we'll get started in a few minutes with trivia. Huh? Because Bo showed up, yeah. But you can help grade. I do. I need you for moral support, so thank you for coming. I need my moral support too. There's two of you that can fill that up. All right, hello again. I'm still just as loud as before. Once again, if you want to play trivia, but you don't have a sheet or golf pencil, you can come get one in the front from Bo. For those of you who don't know, I say this every single time. For those of you who don't know, this is Astronomy on Tap. And we're going to start with a quick 10-question round of trivia. So for each question, I'll put it up on the screen for 30 seconds apiece. At the end, I'll go back through all 10 questions, but only for 15 seconds apiece the second time. So you get 2 opportunities to write your answer down. After that, we will collect all of the sheets and golf pencils, and we'll get started with our first talk of the evening, which will be by Professor Jessica Werk. I will introduce her more when the time comes, because I don't want to ruin the trivia question answers. Okay, does everybody feel confident that they're going to win? That's good. It's good to set realistic expectations. Okay, let's get started. Are you playing trivia? Quiet. I can't tell you.
Okay, cool.
I think it's the gallbladder.
I don't think it is because I know there's no D's.
I mean, the gallbladder is like a very common space term.
Of course. Every astronomer that's worth their anything knows it's the gallbladder.
Wait, what? What a weirdly worded question.
Answer it.
Why aren't there more than two options?
Because it's true or false. Is the
You
statement
came up with
true?
something else.
This Ben came up with this one, man.
I'm gonna go with true, but like I kind of don't understand the question.
The question is like wherever we are in the Milky Way, did we start here?
That's not like a question. Did we start here? Is a question. Why isn't there
You know
a
what,
question?
Sam? You know what, Sam? Wherever you go, you take yourself with you. It's wise words.
I have no idea.
So yeah.
It's gotta be within walking distance. Like,
What?
it's gotta be within walking distance.
I'm gonna go with B just because I haven't done it.
For sure within walking distance. Like a couple times. Every morning.
I don't know this shit.
So guess. You're not even writing down your
Cartwheel
answer.
Galaxy doesn't even sound right.
You know, I think I'm seeing that maybe D is just joking.
No, that one's the right answer actually. Of course.
Are we in the cartwheel?
Did you just ask me if we're in the Cartwheel Galaxy? I'm sorry. Back up.
Hold up.
Re-say that.
Yeah, are we in the cartwheel?
We better decide now.
Yes.
No, we're in the Milky Way.
Sam.
There you go.
Sam.
But the
You dropped the gong. Can you use that for like trivia?
To
Like,
get
between
people's
rounds,
attention?
Like, gong.
I'm just gonna go with filming. What's a filming?
You'll find out today.
That's for me to know and you to find out.
Yeah.
That's for me to pretend I know and for you to find out.
That's for me to vaguely know.
Yeah. I'm sitting in a group meeting like, I definitely know what that is.
Tom Lag.
Yo!
Yeah. It's for sure Tom. Shadow.
I mean, he is head boy after all.
He was head boy. He's definitely like qualified for the role.
Yeah. Very current picture of you.
I just pulled it off the UW website.
Just walk into our office, Jess, taking a picture of you.
Oh, that. Whoops.
Oh, huh.
Don't worry about that. That was a mistake.
Don't pretend it's a mistake.
This one I wrote. Thank you. I can make it too easy for them. We got a hat in the mix of prizes.
We were just talking about
Whole hat.
3.8 billion years ago, which is the late heavy bombardment of the solar system.
Ooh.
But that's not related to this. I was
not
just thinking about it.
Based off of
You got this there. This one I took directly from your slide.
Okay, yeah, perfect. I was like, yeah, I say this all the time
Yeah.
out loud. I'm gonna say this in my talk.
The last two I took. Yeah.
deep. What does that mean?
About this. Oh, the Hubble Deep Field?
How big
It's
is it?
like how big is the field size of the image? The Hubble Deep Field is the one where they like pointed it to a random part of space and they exposed one of those.
one of those?
Like, if I'm in space, how big is if I'm standing next to the Hubble deep field?
Yeah.
How big?
If I'm standing next to the Hubble deep field. Did you just say 2?
Not this way.
About
I don't even know
this
what a
way.
quasar is.
Scale of 2.
I thought about making that the question, what's a quasar, but I think we did that a few times back. So.
I know that I don't know what it is.
Yeah, I don't think you were there for that one. We did that. The quasar one was like, I feel like at the beginning of the summer, maybe even. Okay.
That's all the questions. So I'm going to go back through all of them for 15 seconds apiece, and this is your last opportunity to get your answers down. If you just showed up and you want to try to rapid fire put answers down, you can try to do that. We have trivia sheets up here.
Yeah. You got 2 seconds left on this one.
Nice.
This is an outlet for me.
Born entertainer. Someone said.
I unfortunately did not unmute you for your yelling. I'm sure it would have translated really well to
Jake! Jake, 2 seconds left. Oh shit. It's too long. You feel confident? You feel like you're gonna win? No?
None of them.
I believe in you.
The only answer I'm confident in is that Tom Wag is not the head honcho.
Who do you think is?
That's about it.
I think when the speaker is talking, is it possible to mute this one but just keep their mic on? Oh, okay, sick. Sick. You're already, yeah. Great. Great. You're way ahead of me. It's like that moment when you're like, you know what, a really cool research project would be to do this, and then it's like, oh yeah, that paper came out 20 years ago. You're like, oh sick, cool. So everybody thought about this already. Got it.
It means that you're thinking the right thoughts. But I also totally would have forgot to do that, so I appreciate the reminder.
Yeah, did you pick a team name? Is Halloween like 33 days away?
I was supposed to pick a team name.
You gotta pick a team name.
Astronomy on tarps.
Astronomy on terms. Astronomy on tings. Don't listen to me, that's
I feel like I'm gonna get like a sunburn on like this side of my face.
Yeah, it's hot, isn't it? In it.
In it.
Astronomy in it.
It is.
That's astronomy. Is that
Alright.
Okay, so it turns out that this is
Okay.
understandable.
Ready to collect? Actually, you should stand there. That way you can also help collect. Yeah.
oh, like
Yeah, give help. Because. Yeah.
put your team in it? I'm leaving.
Oh, I have to do all this.
So we're just gonna.
Wait, why do we grade? Why don't people just grade themselves?
Okay. Well, how do you feel about the trivia? Good. Please, yeah, enthusiasm. Great. Can you please bring your trivia sheets and golf pencils down to the front and give them to either Bo or Sam? Don't forget the golf pencils. Please don't forget the golf pencils.
didn't want to overwhelm her.
Yeah, I appreciate it.
I didn't think this like. You should, yeah, perfect. Oh, perfect timing.
All right, so we will get those graded and we will announce the winners of trivia just before the first intermission, but now it's time to get to our talks for the evening. So at this point, I'd like to introduce our first speaker is Professor Jess Werk. Jess is the current chair of the astronomy department at UW. Yes. We're all very excited about it. And she studies the intergalactic medium, that was right, and the circumgalactic medium, which is like atmospheres around galaxies, which is only slightly less interesting than planetary atmospheres. I'm just kidding. I'm just kidding. So, so with that, I'd like to invite up Professor Jess Werk.
Hello, good to see you all here. And I have to say, I'm so impressed by the cider. I'm not normally a beer drinker, so I wasn't super pumped about coming, and drinking beer. But this cider, the raspberry rhubarb, oh my God. I don't even work for Bickerson's, I swear. All right, so today I'm going to tell you about hold on a second. There we go. About the incredibly violent and tumultuous journey that all of the atoms that compose your body have taken over the last 13.6 billion years. And we call this the cosmic baryon cycle. But from my perspective, I really like to think of myself as an intergalactic immigrant. And my hope is at the end of this talk, you're all going to think of yourselves that way too. All right. So I think to kind of get on the same page, I like to start this talk by just pointing out some things that might be obvious, but to just go through them, which is that when I think about, looking at a beautiful night sky, I think of the sky as a kind of window to the past. Every time we make an observation of a star, of a galaxy, we're capturing it at a certain snapshot in time that some amount of time ago, even our own sun, which is our closest star, is 8.5 light minutes away. That is, during the day, if suddenly, nuclear fusion had ceased, well, probably like 10,000 years ago, but we don't need to go into nuclear fusion, and the sun just went out unexpectedly, this would defy all of our theories of stellar evolution, we wouldn't know for 8.5 minutes. And so, the distances actually get progressively larger rapidly. So some of the closest stars in the sky are about 4 light years away. So the light that's traveling from some of the brightest stars you can see with your naked eye is taking years to get to you, to some of the most distant stars that we can see in our galaxy, 20,000 to 100,000 light years away. If on a really dark night you're out in the Cascades and you happen to know exactly where to look with a pair of binoculars, you might catch the Andromeda galaxy, our nearest neighbor that's actually hurtling toward us and going to collide with us one day, in which case will be the Milkomeda instead of the Milky Way galaxy. That's 2.5 million light years away. So, oh my gosh, so you're talking about distances between stars, thousands of light years, to distances between galaxies, millions of light years. And then, of course, the earliest galaxies that we're even just starting to see now with the James Webb Space Telescope are billions of light years away. Billions! It's absolutely mind-boggling. So, in any case, right, the more distant objects are, the longer ago in time we're catching them. The other part of the story is, I study the intergalactic medium, which you've heard, the circumgalactic medium, gaseous atmospheres. a fundamental component of what I study is atomic or baryonic material. And maybe everybody here, actually tell me, by a show of hands, how many of you feel like you really know what an atom is? Okay, you're pretty humble. That's great. Okay, atoms are amazing. Okay, atoms are the best. Last night, this extremely famous professor, Dr. Katie Freese, was in town giving a Frontiers of Physics lecture on the dark universe. And yes, fine, it makes up, like 95% of the mass energy density of the universe, dark energy, dark matter. It's all very exciting. We have no idea what it is. But baryons, atoms, normal matter, that is what we can see. It's amazing. We can study it and make measurements. And that's why baryons are really the best. Sorry, Matt. So he studies dark matter. But baryons are better than dark matter. I'm just going to say it. Anyway, atoms are really cool. Atoms are mostly empty space, though. Did you know that? Our bodies are made of atoms, pentillions, whatever, septillions, number that I can't even say out loud. Our bodies are made of atoms. And if you imagine an atom, it has a nucleus, it has an electron around it. And maybe some of you said you know what an atom is. You're kind of picturing a Bohr model of an atom in your head with electrons circling a nucleus, and if you know where the electron is, you don't know how fast it's moving, all of these great, exciting things. So if the nucleus of an atom is the size of a baseball, does anyone know how far away the nearest electron is on average, approximately, continuing in the sports analogy? Any guesses? Yeah. Where? Yell it. You're not ready. Okay. You're calculating. Yeah, how far? Oh, a mile. That's too far, but I love that guess. A 100,000 times further away. If it's the size of a baseball, that's a little too far, I think, because it's the size of a football field. Okay, so if the nucleus of an atom is the size of a baseball, then the nearest electron is about a football field away. Okay, which is still crazy because our bodies are made of atoms, which are mostly empty space, by the way. But another reason that atoms are really cool is these electrons are zipping around, they're tiny, they're basically massless compared to the nucleus. And every time they move around in an energy level, they emit or absorb a photon. And those photons, or light, are what we can study to understand what the universe is made of. So atoms are amazing, and I basically count atoms in intergalactic space. And I also want you to appreciate a sense of scale here. And it's just like totally mind-boggling. So on the very smallest scales that we're talking about in terms of an atom, if we're talking about meters, it's 10 to the minus 10 meters. And a galaxy halo is 10 to the 22 meters. That's literally 32 orders of magnitude. That's crazy. That's what separates the size of you from the size of the, I forget what that is. I had it in my notes there, but I forget exactly what 32 orders of magnitude is, but it's meant to just blow your mind. It's absolutely huge. So I'm counting atoms in intergalactic space. I'm counting things on the size scale of 10 to the minus 10 meters in galaxy halos that are 10 to the 22 meters large. I'll tell you how I do it, though. It's really fun. All right. And then finally, the other thing that I want you to appreciate is that the universe contains multitudes. And this was a trivia question here, but this image, this Hubble Deep Field, the classic Hubble Deep Field, was an image taken over 10 nights around Christmas in 1995. And the best thing about this field is that it was actually taken in director's discretionary time. The director of the Hubble Space Telescope Institute, Bob Williams, at the time, was getting all kinds of opinions about what he should do with this amazing new telescope in space. Where should he point it? Point it at this star, point it at this galaxy. And you know what he decided to do? He was like, no, I'm gonna point it at a patch of sky where there's nothing, in between all the sky. Where there's no galaxies. I'm going to point it at an empty patch of sky and just stare at it with the most powerful telescope. And what they found is absolutely stunning, which is that this field, which is approximately the size of a grain of rice held in an arm's length, right? A grain of rice held at an arm's length, that there are more than 3,000 galaxies in this one image. And if you add up how many grains of rice you can hold at an arm's length for the entire night sky, you're instantly led to the conclusion that there are billions of galaxies in the observable universe. Billions of galaxies, each galaxy with hundreds of billions of stars. Whew. All right, so anyway, it's absolutely mind-boggling, and I love to think about this kind of stuff. And so here's a dime. Here's the size of the Hubble Deep Field on a dime. And I just wanted to also give a shout out to the JWST Deep Field, since this is like our modern deep field here. This is even smaller. This is a grain of sand held at an arm's length. But again, just like absolutely beautiful image of galaxies of all shapes and sizes. These galaxies are distorted because it's pointed at a gravitational lens or a large galaxy cluster, which isn't the subject of this talk. And then you can see it here on the dime here, just for scale. And think of, like, the universe is just full of this stuff. It's so beautiful and amazing. All right, so let's just stop for a minute to consider now that we are all on the same page. That here we sit in this room, and yes, we're intergalactic immigrants, but we're also just basically a temporary collection of assorted atoms, right? And maybe, like me, you've kind of wondered where, you know, the carbon in your bones comes from, the calcium in your bones, the iron in your blood. And, you know, it turns out that these atoms in your body most likely originated in really explosive events or, you know, in nuclear fusion processes in the cores of stars. And these atoms that are part of your body, I looked this up, will be part of your body for as little as a nanosecond to as long as about 32 years. So if you're older than 32 years, it means all of the atoms in your body have basically changed over, and you're like, you could be a totally different person from who you were when you were born. I'm sure that's the way that works, right? All right. And so, but these atoms in your body, they're not yours, right? They're continually being exchanged with the environment around you. And my favorite analogy with this is this one. Okay, so everybody take a big sip of beer first. Okay, perfect. Now, take a deep breath. All right, you've filled your lungs with about 1 liter of air. Now, get this. There are more atoms in a single breathful of air than there are breathfuls of air in the entire Earth's atmosphere. Okay, so it's kind of crazy. Just pause for a minute and think about all the breathfuls of air that there could be in the entire Earth's atmosphere. And there are more individual atoms in that single breathful of air than there are breathfuls of air in the entire Earth's atmosphere. So what that means is that in that last breath you just drew in, it contains at least one atom in common with the first breath you ever drew as a human being on planet Earth. Even if I grew up in Connecticut and here I am in Seattle, there's at least one atom in there that's the same atom as when I was a baby. Or dinosaurs, people like, or Julius Caesar, that's one that you can find online. Anyway, all right, so just as the atoms on this planet, in the air that we're all breathing here at Bickerson's Brewhouse, have been being recycled into different forms over, you know, the history of the Earth, so have they been cycling over billions of years on even larger, vaster scales in and outside of our own galaxy. And that is the cosmic baryon cycle. All right, so let's talk about how these atoms were first formed. And it turns out that, you know, the vast majority of them were actually formed during, you know, the very first moments of the universe. In a process called Big Bang nucleosynthesis, shortly after the Big Bang. And what you're seeing, who knows what this image is of here, by the way? Anybody know? Who's not an astronomer? All right, who in the back? Tell me, with your hand up. Yes, it's the cosmic microwave background. And this is basically when, you know, photons were released 300,000 years after the Big Bang. The universe had cooled enough that photons could stream freely in the universe. And we get this image of the baby universe, of these, you know, tiny little temperature, you know, fluctuations in the early universe that ultimately become some of these large structures like galaxy clusters. So anyway, the atoms, the lightest atoms, so helium, hydrogen, lithium, a tiny bit of beryllium, formed during Big Bang nucleosynthesis. But then the universe cools so much that it can't form any more atoms. So we were talking about carbon and maybe oxygen and interesting atoms, right? And so most of those actually formed in really different kinds of events. And I really love this. This is the astronomer's periodic table here from Jennifer Johnson. And what you see is the periodic table that's color-coded by, where most of the, where atoms came from. So you can see hydrogen up here. It mostly came from Big Bang nucleosynthesis, Big Bang fusion. But, this carbon, right? The vast majority of the carbon comes from these dying low-mass stars. It's fused in the cores of low-mass stars that end their lives in these, explosive phenomena that are absolutely beautiful called planetary nebulae that expel all their carbon out there, and that carbon somehow gets, wrapped up in another formation of a star like the sun, for example, and then into your body. And also, let's take a look at another one of my favorite elements, oxygen, right? So we've got oxygen. Where is oxygen? Why is oxygen not on here?
Next to nitrogen.
Where is nitrogen? I can't see anything on this plot.
Next to carbon.
All right, whatever. Oxygen forms in exploding massive stars. Let's just be clear. I can't see anything on this diagram, by the way. Yeah.
We're trying to get a new one.
It should be there. Oh, 8. There it is. 8. Number 8. Oxygen. Exploding massive stars, which end their lives in these violent processes like supernovae. All right. So, right. You've heard the phrase from Carl Sagan, we are stardust. And we've talked a little bit about now the atoms in our body and our breath. And yes, okay, so Big Bang, cores of stars, but we're not inside of a star, right? We were formed inside of a star, a lot of the atoms in our body, but how did we get out of the stars, right? Well, these stars end their lives in these massive explosions, some of my favorite of which are supernovae. And supernovae involve this huge collapse, an incredibly rapid collapse when these stars are fusing elements in their core, generating energy and pressure, but they suddenly get to iron. And when you start trying to fuse iron, it actually doesn't generate any energy. It sucks in energy. And then all of a sudden, you're not able to support yourself against gravity and you collapse. And it triggers this crazy explosion. And the elements get spewed all over the interstellar medium. And the interstellar medium is gorgeous. This is a JWST image of a star-forming region here, and you can see these peaks and valleys in the beautiful gas and dust surrounding a young star-forming region where many of these massive stars used to exist here. They died, and they expelled their materials out into the interstellar medium. But I said we're intergalactic immigrants, so we've got to get outside of a galaxy. It turns out, and I bet nobody can read this. Oh, no, maybe you can read this. This is M82. I was going to ask you which galaxy this was. But anyway, this is M82, one of my favorite galaxies. But it turns out galaxies, because all these exploding stars can cluster in the galaxy, they'll all explode kind of at once, and they'll generate a huge amount of energy, which drives what's something called a galaxy wind, where it looks like the entire galaxy is just exploding. So all those atoms that are generated in the cores of massive stars are propelled outward in these massive galaxy winds into the atmospheres beyond galaxies. And so this is called the circumgalactic medium. Some of them get outside of the circumgalactic medium into the intergalactic medium. This image here is from a simulation called Illustris TNG. And this is just if you could see the entire, megaparsec, a slice of the large universe, where each tiny little blob here is several different galaxies kind of exploding with winds, and they're connected by these filamentary structures with little galaxies kind of sprinkled throughout them. This is the cosmic web, and our baryons, get expelled, and then they travel along this cosmic web, and maybe they make it into galaxies, right? So you can run simulations of, star formation histories and galaxy evolution and these winds, and you can theoretically figure out, matching with observations, that basically more than half of the atoms in your body right now probably were generated in a galaxy other than the Milky Way, in a star that was in a galaxy other than the Milky Way, which is why we're all intergalactic immigrants. All right, So, right, they get out of a galaxy, but then how do they get back into a galaxy? This is what I spend a large part of my career actually arguing about at conferences with people. Is like, how does gas, when it's like really hot outside of a galaxy, fall back onto a galaxy? And I'm not going to bore you with all of the physics of gas cooling and the many ways that this can happen. But one way to envision this that I kind of like is precipitation. So just like our own Earth's atmosphere, right? Like it'll get, you know, a bunch of stuff kind of up in it. It'll condense and it'll rain down onto us. You can imagine like galactic rain in these tiny little droplets falling back onto the galaxy and then getting caught up in another event which forms a star, perhaps a star much like the sun. And in the process of creating that star where everything is rotating really, really rapidly, perhaps those atoms end up on a planet 93 million miles from its planet star and into some kind of life form that inhabits that planet. And so, like I said, we're all intergalactic immigrants. And in the last, 10 billion years of our galaxy's evolution, we're breathing the air that dinosaurs breathed, and anyway, the same atoms that were involved in our planet's formation 10, however many billion years ago it actually was. It was like 4 billion years ago, probably, yeah. All right. So the last thing is, I told you I count atoms in space, so I want to tell you how I do that, but I also want to honor the time because I've been up here a while. I'm good. Okay, good. So how do we observe the cosmic baryon cycle? So it turns out it's really hard to observe this. I was talking about atoms, right? And there are these little electrons out there moving around, emitting and absorbing photons. Well, because of the nature of atomic physics, the vast majority of the photons emitted and absorbed by these atoms in intergalactic space are ultraviolet photons. And what's really great about the Earth is that we have our own atmosphere that we can breathe, and it allows us to live. And turns out it actually blocks a huge amount of UV photons. So if you're an astronomer that wants to count atoms in space, and in particular, you want to study ultraviolet transitions of these atoms that are out in intergalactic space, you need a telescope that's outside of the Earth's atmosphere. So that's part of the reason why this is actually really hard, is that you need to use a space telescope. The other reason is that this material is so diffuse, because we were talking about these distances between galaxies are absolutely huge. So they're, expelling atoms, but the density of atoms is so small, you can find there's less than 1 atom per cubic meter in these kinds of spaces. Like you can imagine, you can picture a cubic meter, imagine 1 atom in there. Think about the atoms on Earth, that's like 10 to the 26 times more dense than what they are in this medium that I'm trying to study. So that means it's also really hard, and you need to design really clever experiments in order to count atoms in space. So it turns out there are these objects called quasars. Quasars are amazing. Quasars are so bright, they emit a huge, what happened with this envelope here? Wow, okay. So there are these huge supermassive black holes in the centers of galaxies, and they emit thousands of times more radiation than all of the hundreds of billions of stars in the galaxy itself. And what's really nice about them, because they're so bright and so luminous, you can see them over really large distances. So they're like flashlights in intergalactic space. And so what you can do is you can point a telescope at this really bright object and take a spectrum of it. Has anybody here heard of a spectrum before even? Okay, some of you. So, okay.
You guys have.
You have heard.
Yes.
Okay, the easiest way to imagine a spectrum is have you seen a rainbow in the sky before? Yes. Okay, that's a spectrum, right? That's a spectrum that's caused by the droplets of water in the Earth's atmosphere. But what that means is it's spreading light out over different colors, where color is just the energy of the light. All right, so you can take a spectrum and you can have an actual instrument that generates a spectrum for you. And we take spectra. You've heard the phrase a picture is worth 1,000 words. Kind of heard that? Probably you've heard that. All right. Well, I think a spectrum is worth 1,000 images. Spectra are so great, right? Like they separate that light into its individual wavelengths, which allows you to count atoms. All right, so if you take a spectrum of a quasar, this is a quasar's rainbow here, it looks like this. It's really bright. This is called a continuum. It's really bright over a lot of different energies or colors, and it has these emission lines here. But here's the thing. That's what it would look like if you were standing at a quasar. And if you were standing at a quasar, you would die because it's emitting more light. But imagine you could stand at a quasar. That's what it would look like. But actual quasars, quasars that were discovered in the 1960s, 50s. Oh, 1958. It was on your slide. I don't remember my slide. Sorry, in the 1950s. Sorry. They had a heyday in the 1960s. And the spectrum that I'm about to show you, I'm sure this was taken in the 1960s. But anyway, you see this. It looks ugly, right? Well, you think it looks ugly, but that's actually really beautiful. Every single thing here, that's not like a noise spike. That's not interference. That's not... Every single one of these dips is caused by an electron in an atom that has absorbed a photon at that specific energy. And it turns out you can take this like a fingerprint and determine which specific atoms at what specific times in the history of the universe absorbed the light from this quasar. And that is how you count atoms in intergalactic space. If you don't like that, there's actually a movie here. And so this is just showing you a ray of light traveling from the quasar, going through these clouds in intergalactic space. And every time it goes through a cloud, right, it absorbs. Most of these lines are just hydrogen lines, actually. But you go through a galaxy and you get metal lines from like carbon and silicon and stuff. And this is how a quasar spectrum builds up. Quasar spectra are the best spectra. They're really, really awesome. And a game changer for quasar science was this new instrument that was installed on the Hubble Space Telescope called the Cosmic Origin Spectrograph. I don't know if you guys, who remembers the Hubble resurfacing mission in 2009? Oh my gosh, I love that you remember that. For me, that's like what made my career, basically, because I was getting my PhD in 2010, and the first data from this new instrument that these astronauts installed on the Hubble Space Telescope was coming in right after I got my PhD for my first postdoc. I got to work on data from this cosmic origin spectrograph of spectra of these quasars, ultraviolet spectra of quasars. And this was a super sensitive UV spectrograph that they put on the Hubble Space Telescope. Anyway, fast forward however many years it was since 2010, so, 14 years later, I have a squad. I have a group of student quasar absorption diagnosticians at the University of Washington, and they leave no absorption line unidentified. And the spectra of now thousands of quasars that have been taken with the Hubble Space Telescope, and we count all of the atoms in intergalactic space, and we're determining what the universe is made of, and we're characterizing and quantifying what we've been talking about, which is this cosmic baryon cycle. And so, in conclusion, many of you have seen this t-shirt, pictured here. How many of you have seen this t-shirt? How many of you have this t-shirt? I want this t-shirt. I think it's really nice. It helpfully points out your location in the Milky Way, approximately 8 kiloparsecs from the center of the galaxy. I have no idea how far that is in light years, because I don't think in light years. But we are located in the Orion Spiral Arm, approximately 8 kiloparsecs from the center of the Milky Way galaxy. And this t-shirt's super helpful. You walk around with it, it's like you let people know right where you are, right? Well, I've got a better t-shirt idea, which someday I'm really gonna make. And it's that sometime between 6 and 10 billion years ago, the majority of the atoms in this tent in your bodies were out here, outside of the galaxy. And I hope if you have one thing that you take away from this talk, it's that you are all intergalactic immigrants. Thank you very much. I'm told I'm allowed to take questions, which are my favorite part. So please ask questions. I love questions. Okay, and I'm just gonna point at you and, okay, you.
The spectrograph and then the little animation as the light travels across it.
Yeah.
Why is the spectrograph moving?
Oh, such a question. Yes, I love this question so much. I regret not telling you why now because it's like the coolest possible reason. Does anybody know why? So the universe, yes.
Because it's expanding.
Yes, the universe is expanding. And so what that means is that light that's further away, right, has to travel further. So the more distant those gas clouds are, right, the more red-shifted they are in the spectrum, right? They're just shifted because the universe is expanding. Yeah, it's a beautiful, it allows us to count atoms in space. It's like one of the fundamental tenets of, thank you for asking that question. Yes.
Hi. This is a boggle question. A boggle question is one where it doesn't make any sense at first, and it makes sense after you think about it.
Okay, ready.
So the boggle question, and it's in the context of spectroscopy.
Gotcha.
Okay. What is the speed of dark?
Whoa.
Boggle. Take a moment.
Okay. I know the speed of light. 3 times 10 to the 10 centimeters.
Wait, you just got it.
Yeah. Oh, it's the speed of light?
Yeah, because it's the speed of the missing light.
Thank you. I love that. Thank you for asking that question. All right, great. Whew. Oh, that's another really good question. It's approximately, okay, you have to give an expansion in terms of 70 kilometers per second per megaparsec, approximately. But that's actually controversial. People argue over this too, how fast the universe is expanding. It's called the Hubble constant. There's a big controversy surrounding it right now. I won't go into it, but it's 70 kilometers per second per megaparsec, and I cannot instantly put that into Earthling units. It impacts measuring atoms. Mostly, it actually doesn't impact like individual atoms that much itself. But what's really great about it is it's like the atoms are out there, right? And they're at a certain distance from us. But you can imagine, like, when you think about the universe expanding, imagine an atom is like a raisin in the bread of the universe that's baking in an oven and all expanding. And everything is moving away from everything else at that exact same speed, 70 kilometers per second per megaparsec. So what that means is that when you look at things that are more distant, the light that you would expect, okay, let's take an atomic transition. Let's take a hydrogen atom, right, with an electron in one of its states, and it undergoes the simplest possible transition, which is a Lyman alpha transition at 1215 angstroms. If you observe that at one particular distance on Earth, it's 1215 angstroms. But if it's a little more distant, right, its wavelength is going to change based on how far away it is from us in terms of this expanding universe. And so it kind of shifts things relative to each other in this wavelength space, which is why spectra are so powerful in this context. Yeah. Yes?
Between the origin star event, whichever, and whatever gravitational well the atoms will coalesce into to form large solid objects, is their trajectory guided by gravitation or electromagnetism, or is it mostly straight shot?
Whoa. Okay, yes and yes. I'm sure I don't think it's never going to be a straight shot. But that question, I think, is like the heart of the research that I do on the cosmic baryon cycle. And there's a lot of physics that go into it. I think, you really have to understand how gas is moving and what temperature it is and what density. And those are the kinds of things we're trying to measure and then work with theorists to understand. So it's a great question. I don't really know the answer, though. I wish I did. Yes.
Atoms are coming from exploding stars. What's the variability between different types of exploding stars? Do they have emit the same kind of atoms, or is there a difference between this kind of?
Yes, there's a difference. There's definitely a difference. I'm not an expert in that, but some of them are like hydrogen rich. Some of them don't have that much hydrogen. So anyway, yes, there's a difference in terms of what they call it a progenitor star. And the different progenitor star makes a big difference in terms of what's all in there. Yeah, the mass of the star primarily, and when the star formed, right? And how many, so, okay, everything heavier than hydrogen and helium in the universe is called a metal. And so where a star formed, its particular location can have a different abundance of different metals, and that'll totally dictate what's in the explosion. Yeah.
One more question.
All right, one more question. I'm allowed one more question.
Will you repeat the question?
Yes, I can repeat the question. Yes, thank you. Right there.
So, it sounds like this is relatively new work you're doing.
Relatively.
Can you make any conclusions or, summaries about what you found so far? Is like the distribution of matter kind of like the CMB? Is it uniform or is it weird? Pocketed certain ways?
Okay, so the question is, what have I found so far in my research and how can I kind of summarize that? And is what I have found weird? Okay, so I think, oh God, there's so much I could tell you, but I'm gonna try. The first thing that comes to mind, okay, is so I look at the gas outside of galaxies and what matters the most for how that gas looks in terms of its composition and its like temperature, density, is that galaxy forming new stars when we observe it or not? And if that galaxy is forming new stars, you see a lot of stuff. And if it's not forming new stars, you don't see it as much, and it's probably in like X-rays or something.
You can age galaxies.
Wow, I haven't tried that yet, but I'm going to. Thank you. Thanks, all. Thank you so much for the good question.
Matt and yep, okay. All right, let's give Jess one more big round of applause. Okay, so at this time, I get to announce the trivia answers and the trivia winners, and then we'll do an intermission. We had 2 winners of trivia tonight who got 8 out of 10 questions correct, which is pretty good. That's a passing grade. And I forgot to mention this at the beginning, but we actually have some new trivia prizes. So, surprise. Okay, with that, first question. Intergalactic is between 2 or more galaxies. The what? Oh, you nailed it? Hell yeah. Okay. We are in the Orion arm of the Milky Way. It is true that whichever part of the Milky Way we're in, which is the Orion arm, we didn't exactly start out at this location because we're intergalactic immigrants. Got it. The Milky Way is 26,000 light years away from us, the center, or in other words, 8 kiloparsecs. The Triandium galaxy is also in the local group with us and Andromeda. The local group is in a filament between the Virgo and Fornax clusters, to be very specific. Jess Werk is the current chair of the astronomy department at the University of Washington. Yeah, applause, absolutely. Absolutely applause. This is a recent development. Okay. Approximately 400 million years after the Big Bang did the first galaxies form. Fun fact, the first one is atoms, the second one is stars, the third one is galaxies, and the last one is nothing, actually. And then the Hubble Deep Field is about the size of a grain of rice at arm's length, which is about this big. And finally, quasars were discovered in the 1950s, according to Jess Werk's PowerPoint slides, which I did not verify, by the way. So, I think it's right. So, with that being said, our first trivia winner is Just Okay. That's literally the name. Who was it? Great. You did better than Just Okay. And our second trivia winner is Spaghetti. Nice. But you're sitting with Jess. That wasn't...
Team effort.
Okay. Whoa, whoa, whoa. Okay, sure. We'll verify that in the intermission. So with that being said, we're going to take a quick 5 to 10 minute intermission, and then we'll come back with Professor Matt McQuinn for our second talk. I'm going to get welcome back to Astronomy on Tap. I am just as loud as ever. Thank you so much for being here and for preparing yourselves for the next talk. So, I'd like to, get serious for a minute. For our second talk of the evening, Professor Matt McQuinn is here to respond to the allegations that baryonic matter is better than dark matter and energy in the universe. This is being recorded, just so you know. So, Professor Matt McQuinn is a faculty member in the astronomy department at the University of Washington. And I aced his class, so that's another fact about him. And so with that... Oh, thanks, Jess. So with that, I'd like to introduce Professor Matt McQuinn.
Thanks so much. This is going to be a tough act to follow from our esteemed chair. Right. But this talk is definitely going to be a little bit more out there, but there's going to be a fair amount of overlap, but the overlap is on really cool stuff, so hopefully that's okay. And we're going to start off in a similar place to where Jess started off, which is the universe is like crazy big. Like we look around, like we can see, for example, with this James Webb Telescope, the galaxies. Wow. That are so far away whose light has been traveling since almost the beginning of the universe, and actually because the universe has been expanding, there are almost 100 billion light years away. So we're able to look out and see 100 billion light years away, and we can even see a little bit further if we look at 1 centimeter wavelength radiation, which is most of the light in the universe. And this is light from remnant light from the Big Bang, the cosmic microwave background. And when we do this, when we look out at galaxies in different directions and look at the cosmic microwave background, one thing that we see is things look the same in every direction. We think just like there are Milky Ways around us here, or galaxies that look like the Milky Way, there are galaxies that look like the Milky Way 100 billion light years away. The universe is very similar in every direction that we look. And then if we keep using our favorite unit, light years, and we measure, for example, Jess's height, then Jess's height in light years is 16 zeros and 1 light year. So it's super small compared to the size of the universe. I'm an astronomer, and so I only keep 0 significant digits. But at the same time, Jess is super big. Like if we measured her in atoms, she would be 1 billion, billion, billion times 10 atoms, or 10 to the 28 atoms. So lots of atoms. But you might say, okay, an atom is small. Of course an atom is small. Just emphasize that an atom is small. It's 1 billion, billion, billionth of a light year. But actually, in our particle accelerators, we're able to measure things that are 1 trillion times smaller than an atom. And we actually think that it makes sense still makes sense to measure things, that there should be structures in the universe down to a billion, billion, billionth of an atom, which we call the Planck length. And below that scale, when we try to measure things, with whatever we're measuring, our measurement apparatus will become a black hole. So we can no longer measure distance. Distance no longer makes sense. But relative to the smallest scale, an atom is huge. And so it's just crazy how much information is in the universe. Like how many units, Planck units, like the number of Planck units that fit into the size of the universe is like truly astronomical.
Well, of course. Good one.
Yeah. But it doesn't have to be that way, and we're going to get to it. And actually, this whole talk is about, our universe, it's actually not that big. the universe is actually way, way, way bigger. And I'm going to give you some arguments for why that's the case. And these arguments for why it's the case, they're often the bigger universe, the bigger than we can ever see, further than the things that further away that has been able to travel to us in 14 billion years. This is called the multiverse. And so I'm just going to start off by telling you we actually know that the universe is a lot bigger than what we can see. And I'm not going to go into the details. This is actually a previous Astronomy on Tap that I gave a couple years ago. But we have this like amazing theory that's kind of cosmologist creation theory. It's not like how the universe was created. Science really we don't think can answer that. But it's a theory for how the universe was seeded, how structure was seeded, how the structures that grew into galaxies, planets, humans was seeded. And we call it inflation. Super successful theory. It explains a lot about our universe. And one thing that happens, there was a second movie. But the movie was a not very interesting movie. The way inflation happens in our theories for inflation, the part of the universe that we occupy is so much smaller. And in some of these models for inflation, the universe varies hugely on scales that we can never see, like much further than the size of the observable universe. And almost all cosmologists, astronomers are subscribe to this theory. It's like it's not a controversial theory. So we already know that the universe is a lot bigger than what we can see. But I'm going to give you an argument that the universe may even be bigger than this, which is that like when you look around, and I'm going to give you a lot of examples, and I'm only going to give you the astronomical examples, the cosmological examples, and there's actually a ton of other examples. There are just so many things that seem designed. Some of them having to do with gas around galaxies, the circling galactic medium, that seem like they've been tuned for us to exist. And I'll explain how this might indicate that the universe is way, way larger. All right. And I'm going to start off with the same picture that Jess showed, which is actually the most beautiful picture that was ever taken. This is a picture of the cosmic microwave background, as Jess mentioned. This is the baby picture of our universe. So cute. This is when the universe was 400,000 years young. How do you interpret this picture? You're used to seeing a map that looks like this. It's usually of the Earth. And this is North America, South America, Europe, Asia, Africa. But the Earth is the surface of a sphere. You can turn that around and just make the sky. The sky is also, you can put on the surface of a sphere. And so every pixel on here I'm really bad at this. Is light that has been traveling for 14 billion years. And so some regions, there's a little bit more light. It's not a lot more. And others, there's a little bit less. These are the seeds of structure that grow into you. These small seeds. And 99% of the light in the universe is this. This is 1 centimeter stuff that you can't see with your eye. The reason I'm telling you this is we're doing the Cosmology 101 in 2 minutes. So this is actually cosmologists' favorite thing, the CMB. We learn most of what we know about cosmology by studying this. People then take this image of the CMB, these small fluctuations, which indicate that there's some more matter in one region than another region, and they put it on a supercomputer. And on large scales, in the universe, the strongest force is gravity, and gravity pulls things together. And so when you put this on a supercomputer, these small seeds of structure that we see when the universe is 400,000 years old, they grow and they grow, and then they eventually start to look like structures. This is when the universe is 3 billion years old, so it's not quite to today. It'll eventually get to today, but I'm going to change the slide before it does because this movie is actually quite long. And you can see that there's like a bunch of structures, and these structures, when you zoom in on them, some of them actually look like the Milky Way. And so we take these images of this cosmic microwave background, we put it on the computer, we run it forward knowing with the laws of physics that we understand, and we actually get a universe that looks a lot like the universe that we see, that Jess observes in her spectra. Not exactly, Jess will tell you, but that's a different story. Okay, why am I telling you this? Well, we're going to start now talking about if we change like little things, it no longer works. The life as we know it, life in the universe can go away very easily. And so one example of this is we have these seeds of structure that we see in this background radiation from the Big Bang. The sizes of those structures, how much stuff is in one place in the universe versus another, are just right that they can grow into this astronomy on tap. Whereas if they were a little bit smaller, you actually wouldn't have very many galaxies in the universe, and actually not even that much smaller. Or if they were a bit bigger, the universe would just be a lot more chaotic. If they were quite a bit bigger, the universe would actually be all black holes. And so we're very lucky. Like, the universe is right so that we can have these Milky Way galaxies where we can sit at a pub and drink beer. But I've even got ahead of myself, which is that in our theories for how particles work in the universe, there's always a particle and an antiparticle. This always has to be the case. This is just because of how physics works. We even know that this was the case. Like if I have an electron, we see positron. That's its antiparticle. We can even tell. So when the universe was 1 second old, there were 1 billion times more electrons in the universe, but there are also 1 billion times, or the same number of positrons, which is 1 billion times more than the electrons currently. So there were so many positrons and electrons when the universe was 1 second old. This was when we just mentioned Big Bang nucleosynthesis. This was right around that time, when we were forming helium and in the universe. And we see this. We actually have observations of the universe when it was 1 second old. It's crazy. But actually what happened is the electron found every positron, and they don't like each other very much. And so when they hit each other, they go into a lot of energy. And so this happened really sadly for all but 1 part in 1 billion. Because there was a small asymmetry at this time in the universe where there was slightly more not like actual matter than antimatter. And this slight asymmetry is very important because otherwise we just wouldn't have atoms. They would have all gone poof. And so we're lucky, and we don't actually know why this was the case, because so there was something in how particles work that created this asymmetry and allowed us to exist. Okay. Moving on to the best type of matter. It actually turns out you would not exist if there was not dark matter in the universe, which is surprising. So there's 5 times the mass in dark matter in the universe compared to atoms. This is very important because remember, when the universe is 400,000 years old, there's so much energy in this light that we see in this cosmic microwave background. 100 times more energy in this than all light ever afterwards. And it really likes to grab onto electrons. It loves electrons. And so when it grabs onto electrons, this light moves really fast, just apparently like dark. And it pulls all of the electrons, and then the electrons, pull the nuclei, and this destroys if there was more electrons in one place and less in another, it wipes this out. Now remember, more in one place, less in another. This is what you need to grow structure. This seeds the gravity that we saw in that movie. And so it's actually in that photo of the cosmic microwave background. If we could see the atoms in the universe, you would see that their fluctuations are very small. But if you could see the dark matter fluctuations are much larger. And what that means, remember that if we didn't have the right amount of fluctuations in the amount of matter from place to place, you wouldn't have galaxies, you wouldn't have structure. And so this dark matter, because it has much larger structures, the amplitude is bigger, it's essential for galaxy forming. If the universe only had atoms, it would be a much worse universe. Hence, dark matter is the...
If it only had dark matter, though.
You need both, at least. You need both. So you guys wouldn't exist without dark matter. Weird. So another thing that we need. This gets to this messy atomic physics that Jess's talk was on. Someone asked, does gas just fall into the galaxy? And Jess said the answer is no. It's complicated. One thing that does happen is atoms do have a property that dark matter does not, and it relates to the fact that light likes atoms that we had mentioned, which is that if I have an electron, I have something go by and bump it, like another electron, and let's say the electron is bound to a nucleus, then it can jump up and fall back down in the atom, and this emits light. And when this happens, the atom this loses energy. So the atom will cool off, and if it cools off, it has less pressure. And this allows it a bunch of atoms to become denser because they're not able to support themselves as much. And so the atoms, they lose their energy. The dark matter, this does not happen to. It doesn't like light. It doesn't emit light. And so the gas loses its energy and it cools. This is called cooling, the losing of energy. And this is why you have galaxies. And this is actually why galaxies don't have a lot of dark matter. The dark matter is on a much larger scale. The gas is able to lose its energy. Actually, this losing energy is really important, not only for galaxy, it keeps losing its energy, and eventually becomes stars and planets just by letting out light. And not that planets are the most interesting thing to study, but that's basically the story. But okay, it turns out that this would not happen if the mass of the electron were significantly different. So the electron is the most important thing for emitting energy in the universe. If it were a lot heavier, there would be a lot harder to do this excitation of atoms. Additionally, if it were, and not even a lot, somewhat heavier, and so the atoms wouldn't be able to radiate photons and lose energy. Similarly, if it were a lot lighter, the electron would not bind to atoms. There wouldn't be atoms. And so it turns out that our electron is just at the right mass so that this can happen and so that we can get planets. Why? I'm going to skip that one. There are many arguments that you can reframe in this. This is another argument, which is, as Jess talked about, like stars, they explode, they're complicated, they synthesize nuclei that are heavier than helium. It turns out that a crazy amount of stuff has to go right for for many of these things to happen. In fact, one of the famous ones is that in order to get heavier elements than helium, the Big Bang produces some trace amounts of stuff. But like to get substantial amounts, like to get carbon, you have to quickly move 3 helium together, and combine them. This is called the triple alpha resonance. And it's like when physicists were first thinking about this, they thought there's no way this is ever going to happen, even in a star, unless there's some mysterious thing that some resonance that enhances this process. So it turns out actually there's a resonance that makes it so that this process is enhanced so that you can actually get carbon and heavier elements. Otherwise, you couldn't do it. There's a desert of nuclei. And actually, this was one of the first arguments for why our universe seems like it's tuned. There's this mysterious resonance, and it's very easy if you just change anything, change electron mass, change charge. This would go away. And you could go on and on. If you just change any physics, or if you change the masses of quarks, you would totally change nuclear physics. The neutron is only slightly heavier than the proton. But if the proton were heavier than the neutron, it would decay into neutrons, and then you just have a neutron universe, which would suck. And then just these exploding stars, everything has to go right for a star to explode. And so if you just change anything, it seems like they wouldn't explode. And so it's kind of amazing how many things seem tuned for our existence. But actually, the most famous example is with dark energy. How much energy density in the current universe, of all the energy in the universe, how much is in something that's called dark energy? Anyone? Yeah. Wonderful. More significant digits than I even know. That's yes, 68% is what the gentleman said. So 68%. Okay, so dark energy is this really weird substance. It unlike anything else that we know of. Yeah, so I think so. Most things that we know have positive pressure, like this air, it'll push if I squeeze on it. But dark energy will actually pull. It has negative pressure. We think it's the energy of the vacuum of space. And actually, our theories for particle physics, which are super successful, predict that there should be energy of the vacuum of space just from particles appearing and disappearing very quickly. You can't really see it. But they predict that the dark energy should have an energy density that's 120 orders of magnitude larger than it actually is. This is considered the most embarrassing prediction in physics. This is despite these theories for particle physics getting everything else right, to 15 decimal places in some cases. But somehow they predict that this should be some crazy large thing. This is actually also the reason that the universe is large. The numbers I were giving you in the beginning. If the dark energy was what we think it should be, the horizon of the universe, the size of the observable universe, would be the Planck scale. So the reason the universe is big is that the dark energy is small. And so our best theory for how this could occur, and this theory has gotten some criticism, but it's our best, is that the universe is crazy large. But in most regions in the universe, the dark energy has a much larger value than in our region in the universe. But if the dark energy has a much larger value, the dark energy is actually what's causing the universe's expansion to accelerate. And so the regions that have a larger amount of this dark energy, you don't get galaxies. So most of the universe has more dark energy than the part of the universe that we're in, but they don't have galaxies. If you don't have galaxies, you don't have humans. You don't have people to observe the cosmos. And so we happen to live in this pocket of the cosmos, this really small pocket where the dark energy is small.
Is there a slide missing?
Oh yeah, oh no, it's okay. I forget what the slide was, so that I feel so it's all good.
I'm sure it wasn't important.
But yeah, so I mean, so and like in the context of string theory, there are ways of realizing this where it's not only the dark energy that that is different from place to place. Everything is different. The electron mass is different. And so maybe this is the explanation. Maybe this is the explanation for why everything seems tuned in our universe. We're in this small pocket of the cosmos where we can exist. And maybe this isn't actually so surprising because this is actually occurring in the observable universe. Like we're not in the intergalactic medium. We're not out of the atmosphere of our planet. We're in this really, really small pocket of our universe where we can exist. So why couldn't this be the case on much, much larger scales? And so that's the proof. I have not got into even crazier things where I think that there's other reasons the universe may be big, but with that, I'll take questions. Thank you. Well, I worried about your question, but
Is it possible that our understanding of how gravity works is false times 10 to the 120th power?
yeah, this is a really good question because a lot of physicists have tried to, rather than explain the value of the dark energy, say, no, we need to modify gravity. Now, you also still have to explain why the dark energy is small, because our theory gives something way larger. But maybe you say it's zero. There's some symmetry, or there's some principle that makes it zero. The issue that we've come up against is that our theory for gravity is the most elegant, beautiful theory that's really hard to change. And so we have not found a way to consistently change gravity. And so a common statement is that we have no good theories for how to modify gravity. Like none of them make much sense.
Well, you don't.
No, so that's right. Like maybe.
Let's move on to the next question.
But okay, let me just.
No question. Is it possible?
Yeah, we've been doing physics successfully for a few hundred years, starting with astronomy. That's where our successes started. And there's a lot of time in the future. And so I think it's possible we'll come up with a better solution.
Jess has a question.
Yeah.
Okay, off the top of your head, what are the chances that there's an exact copy of you 10 to the 120 whatever meters away at the exact same moment doing the exact same thing right now that you're doing?
Can you repeat the question?
Yeah, the question is, what's the probability that somewhere else in the universe there's me giving an Astronomy on Tap talk on this topic? And so I think then this enters into the discussion of different types of infinities. And so even if the universe is infinite, I think we don't necessarily expect that I'm like me here. There's like a lot of atoms. Some of them have been in my body for 32 years that have to be in certain positions and whatnot. And that's a bigger infinity possibly than the infinity of space. And so my argument is not that the universe is much bigger. Is not necessarily that I am doing this here. There are other things.
There could be exact copies of you.
You can't say it's not true.
Yeah, I mean, I think if infinite is infinitely, even a very big infinity, then sure. Yes.
You said that, like, I might have misheard, but that the universe has like kind of a structure to it. How would you classify that or like describe it?
Yeah. So amazingly, this gets to this inflation theory, and why do we even believe? Okay, and the question is, the universe. I said the universe has a structure to it. How do we know that? What is it? And so this inflation theory, which is possibly, other than the things that I said, the most profound. Is one of the most profound theories actually the prediction is that there are these quantum fluctuations that that seeded us. That quantum mechanics, like things are fluctuating. Like if you look at small enough scales, the little like electrons and positrons are actually appearing here and there. And so there's this uncertainty when you look on really small scales. And what happens in inflation is this uncertainty stretches to the size of the universe because the universe expands so fast. And when it does this, it imprints a spectrum of fluctuations in the amount of matter from place to place that is almost the same on every scale. If I take a region that's this big and a region that's bigger, the fluctuations are roughly the same. But it actually predicts that they should be slightly different, which is amazing because we even see this because inflation has to end. And so we, from studying these fluctuations, and they have actually a certain probability distribution. So it's basically that the sizes of fluctuations in a certain quantity, which isn't the density, are the same on every scale, and then those grow via gravity, and generate the myriad of structure. And that's the best I can answer that. Yeah. Yes.
You said the matter-antimatter asymmetry is a part of a billion. How do you know that? How big are these error bars?
So the question is, I said the matter-antimatter asymmetry is a part in a billion. How do I know this? We actually know this incredibly well. The reason we know this incredibly well is that you take this cosmic microwave background energy, which is 3 Kelvin. There's this 3 Kelvin, which means that if I had something that was 3 degrees Kelvin, which is minus 300 almost degrees Celsius, like I had something of that temperature, it would emit radiation, light, with a certain spectrum. And so this light from the Big Bang has that temperature now, which turns out to give it about a 1 centimeter wavelength. So it turns out if you do what Jess was doing, where like as things travel through the universe, light stretches. So this was causing her the spectral features in her to shift to different places. Well, if you run back a 1 centimeter wavelength to when the universe was a second old, it was actually tens of nanometers. Like it was an X-ray photon. And it turns out that these X-ray photons, when they hit an atom, they will start producing electrons and positrons. And so just by running the CMB backwards, we can calculate exactly what particles there are in the universe. This is the same idea of a particle accelerator. We smash things together with certain energies, and we can create other particles. And so you can start to create these. When you smash things together, you'll create a positron just as easily as an electron. And so we see that. And then you could say, okay, how do we think we can calculate it to 5 significant digits or something, how many there are. But how do we actually know that? It turns out that this early universe not only produced light, it produced neutrinos, which is like another light particle. And we can actually measure how many neutrinos there are in the universe. These neutrinos, they have the temperature of the universe when there were 1 billion times of positrons and electrons more positrons and electrons than today. And we can see by measuring how many neutrinos there are, the mass in these neutrinos, we can actually measure we can see that there were so many more electrons and positrons. Cosmology is beautiful. I'm told final question. Yes.
Bring us back to where we are now.
Yeah.
In your slide before, you had like the dark energy that balance with galaxies, and it's an example of fine tuning.
Yeah.
But it occurs to me that we're a mile away from the ocean, so we have the same argument that we're here because the ocean is less than the land at this point. So why is that an argument for fine tuning and not just this is the way it's developed?
So the question is,
Question, I'm sorry.
yeah, the question is that there's a lot of fine tuning. Like even the whales might be in the ocean, but we're on land. Like a zillion things have gone on. I would say that the dark energy is different in that if the dark energy is even like a factor of a few larger its density than today, then the universe is so boring. Like there are just atoms that never see other atoms everywhere. Because you just never, the gravity isn't strong enough to overcome the dark energy. And so the universe then, I think it would be very hard to imagine it having anything that resembles life. So the argument is that, why are we in this part of the universe that we are? Well, this is the place that life can exist or humans can exist, so we can then look out. But in this dark energy argument, all but 1 part in 10 to the 120, it's so boring that that there is no life, and so I think that's the difference. All right, thank you.
All right, let's keep it going for both of our speakers of the evening, Dr. Werk and Dr. McQuinn. Okay, so don't forget if you won trivia to come get a prize. The other thing I want to mention is that our next Astronomy on Top will be on November 20th. There's a really special speaker coming. You might remember that I disappeared for a few months this summer. Well, the person who was advising me on my research over the summer is going to be giving the Astronomy on Tap talk in November. He's the Chief Mission Architect for Science and Robotic Exploration at Northrop Grumman, and he was instrumental in building Chandra, JWST, and now Habitable Worlds Observatory on the horizon, so it should be a really good talk. And the last thing I want to say is that if you are affiliated with the UW Astronomy Department, please come to the front and take a group picture with Jess and Matt so that I can strong-arm more astronomy faculty into giving Astronomy on Top talks. Woo! Thank you. Go home, sir.